comes the importance of electronics for communication. And we also discussed about that we cannot transmit a digital signal because we have to design any circuits of infinite bandwidth. That is not at all possible. So that's why we are going to convert all the signals into analog format. Then only I can transmit it through an antenna. I discussed about that also. And in addition to that, in lab hours, we started discussing about why we should go for digital based circuits. What is the importance of digital circuits in communication perspective? The simplest and the basic understanding is that I cannot store all the values of analog because it has infinite values. That is highly impossible to store all the analog values and process it. On the other hand, if I convert that analog signal into digital, the storage becomes a finite number and processing can be done using microprocessors. So there comes the importance of digital electronics when compared to analog electronics. But you cannot completely neglect analog electronics. At the same time, you cannot completely neglect digital electronics also. Some of the processing is happening in the analog domain, some of the processing are happening in digital domain. As an ECE engineer, we all should be aware about what is the importance of analog electronics and what is the importance of digital electronics. Okay, and if I deal with digital electronics, we in the digital electronics course we studied about basics of AND gates, some multiplexers, combinational circuits, encoder, decoder, mux, demux, priority encoder, many things we have studied, and some sequential circuits also we have studied. Latches, flip-flops, counters, melee and more, finite state machines, sequence detectors we have studied. Using these things, I am going to design a microprocessor which is going to deal with the digital signals. If I need this processing particularly for audio and video processing, then they named it as DSP processors, digital signal processors. Anyway, they are processor means that is going to deal only with the digital signals only, but specifically for audio and video applications for the high accuracy, very high speed, some filtering operations are required means then I go for DSP based processors, very particularly meant for audio processing or video processing. Those type of processors we are going to deal with. The lab codes we are dealing with the VHDL code. What is the importance of VHDL code? Why we are going for programming based approach? Because as the complexity increases, I cannot deal with using paper and pen. I have to write a program that will deal with the, whatever may be the size of the circuit. I am going to just write a program. By writing program, design time gets reduced very much, accuracy increases because when compared to manual drawing of a circuit, if I go by using hardware descriptive languages, the accuracy, the connection problem, we no need to bother because if we are writing the program, the based upon the program you write only, the connections are going to get established. Okay, so once you know the basic of that understanding about that functional block, digital functional block, if you write the program correctly, then you don't need to bother about the connections. That will take care of that. You can infinite number of, I mean, some 1 KB or 1 GB of data also, circuit also, it can easily generate. Nothing to bother about it. So this is what we have discussed in combination with the yesterday's class, both in theory and in lab. And I said yesterday, today I will try to discuss what is the importance of VLSI in this communication perspective. Okay, VLSI in this particular perspective. Okay, first VLSI stands for VLSI stands for VLSI, very large scale integrated circuit. First question we should answer is that where does this VLSI, why should I go for VLSI, what are the different techniques or different types of integrated circuits are there. In order to get into that introduction, but first we should know what is the history of electronics. Okay, always if you know the history, you will have some better understanding about the subject. So I always go in that approach. Okay, we should know how does the electronics evolution came into picture. In the first generation, they are using relay-based design. Relay-based means normally open, normally closed based type, that type of switches. If you provide current to one coil, it will get energized and it will get magnetic field. So based upon the magnetic field present, the switch will get a turn on and turn off. That is normally used in the power meters or in cranes, those places, relay based switches. Till now, it is existing. PLC board switches, many places, relay based connections are existing. Even in our AC, I hope you might be using what stabilizers. Those stabilizers are using the relay switches. If the voltage is low, it will switch on the other relay switch. If the voltage is high, it will switch off the other switch. Like that, based upon the voltage availability, the current will flow. So based upon the current, the magnetic field will get generated, and based upon the availability of the magnetic field, the relay switches will get turned on and turned off. So those are relay based switches. That is the first electronic component I can say. Okay, we are going to control the switches based upon the magnetic field. And then they started in the second generation of electronics, they are going to deal with the vacuum tubes. In the vacuum tubes, I'll be having a glass type of tube will be there. I have an anode electrode and cathode electrode will be there. And the conduction of electrons between the anode and cathode is going to decide based upon the polarity I provided to the anode and cathode. Okay, so the conduction happens based upon the what voltage are provided to the anode and cathode terminal. I am going to conduct the current or not conduct the current based upon the voltage I provided to the two electrodes. So that is about vacuum tubes. And then they started up with the third generation of electronics started when they started using semiconductor based ICs, which means that it can be a diode, it can be a transistors. In transistors also many transistors are there. It can be junction field effect transistors, bipolar junction transistors, mass transistors, heterojunction bipolar transistors. Many such transistors are there. Here they are using electrodes and two electrodes, anode and cathode, for conduction of charge carriers. Here they started using semiconductor based designs. Okay, they are going to they started designing some electronic components like diodes and transistors. They started designing, and these electronic components, semiconductor based electronic components, they started designing circuits. They started designing circuits like rectifiers, clipper, clamper, and some voltage regulators, amplifiers. They started designing using these transistors and diodes. They started designing. Okay, so this is the third generation of electronics evolution. And using these electronic components, if here, for example, in our lab, what we used to have, we will be having a breadboard. I will be placing the electronic components, some diodes, resistors, like that. I will connect them. I will connect them like this. I will provide voltage over here. I will provide current over here. I will check the output what will be the output over here. If I will place some capacitors. So what I am doing in the lab purpose is I am placing the discrete components. Either it can be resistor, capacitor, diode, transistor, whatever I am seeing over there. I am connecting it manually using the wires, connecting wires. Either by soldering or by inserting in the breadboard, I am making the connection, and based upon how you connect it, the circuit is going to work. This is how a simple circuit will work on. But as the complexity increases, simple circuits I can do the manual using breadboard, or by using soldering to some extent I can do the connections. But if the complexity increases, I need more functions to be done. I cannot do soldering for very large circuits and all. So in that purpose, they started putting all the components. It can be an active component or a passive component or a combination of both active and passive components. They started putting in a simple IC. Okay, they started integrating all the active components and passive components in a simple IC. So the circuit is now bringing into one small piece of IC where I have some pins over there. Okay, it can be an SMD package or DL inline package, or many other packages are there. I am not going to discuss all those stuffs. So I'm putting both active components and passive components, putting it in a single piece of IC or in a piece of chip, that is called as integrated circuits. Integrated circuits means it is a combination of both active elements and passive elements are put are clubbed together in a single piece of chip, which has input and output pins over there. Okay, so this is all about integrated circuit designs. So this is how the evolution of electronics started into picture. First we started with relay based, then we moved on to vacuum tube based design, then semiconductor based design, and using semiconductor based designs and active and passive components, I started them to integrate in a single piece of IC. Then this is, we are in this era. Okay, IC based design, and actually I can say fifth generation is also there. System on chip. System on chip means many ICs are put again within a single IC. For example, I have IC1, IC2, IC3, IC4. Okay, each one is an IC. Every ICs are put together in a single piece of IC. So this is a complete system on a single chip. System on chip. Okay, the next era also, when they started coming, and it is all well established at this point of time. Okay, so this is how the evolution of electronics comes into picture. Among this five generation of electronics, evolution of or generation of electronics, I can say that the usage of semiconductor based design plays a very important role in the evolution of electronic components, because can anyone of you say why these semiconductor based designs played a very important role? I said the answer, among the five generations of electronics, semiconductor based design plays a very important role or vital role in the evolution. That is the reason why this electronics has grown such a very huge heights in current trends. Can anyone of you justify why it is happening like that? Any guesses are there, or any idea do you have?
Sir, I think it increases the efficiency of the, like it increases the efficiency, sir, and decrease the size.
Very good, very good. Then any other answers? Okay, I will go with the answer whatever he said. May I know your name, please?
Subhash, sir.
Subhash. Thank you, Subhash. So, first I am going to deal with what are the different types of integrated circuits are there. What are the different types of integrated circuits? So, there are different categories are there. Small scale integrated circuits, medium scale integrated circuits, large scale integrated circuits, very large scale integrated circuits, and an ultra large scale integrated circuits. There are many categories of integrated circuits itself. So how do I classify them as a small scale or medium scale, large scale, very large scale, or ultra large scale integrated circuits based upon how many logic gates do I have? If an IC has up to maximum of 10 logic gates, then I call it as a small scale integrated circuits. If I have if the IC is having maximum of 1000 logic gates within that IC, then I call it as an medium scale integrated circuits. In a large scale integrated circuits, I can use maximum of 10,000 logic gates. In a very large scale integrated ICs, about 10,000 till 1 lakh, 10,000 to 1 lakh, that is grouped under as very large scale integrated circuits. Beyond 1 lakh of logic gates in an IC, I call it as an ultra large scale. Actually, I made a mistake over here. It is ultra large scale integrated circuits. Okay, so based upon how many logic gates do I have, I am going to classify it as different categories of integrated circuits: small scale, medium scale, large scale, very large scale, and ultra large scale. Our course is going to deal with the very large scale integrated circuit design. See here, there is a link between this slide and this slide. I first had discussed about what is the evolution of electronics. Finally, I ended up with an integrated circuits. In integrated circuits, how many classifications are there? And then I finally ended up with one particular term called as very large scale integrated circuits. The answer is why these type of integrations are required, because we need to make the circuit compact, low power, low high speed. These are the specifications I ask when I go for an integrated circuit design. The answers are in the further slides. Please hold on for a few minutes. But We are not going to concentrate on these type of logic integrated circuits, small scale, medium scale, large scale, and ultra large scale. We are going to deal completely with respect to very large scale integrated circuit designs only. So as I said, small scale integrated means it is going to have the range of 1 to 10 logic gates. The basic gates, I hope in your first digital electronics lab, you are using some logic gate ICs 74 LS08, 7404, 32 for OR gate, 00, NOT gate, AND gate. For example, in an AND gate, how many logic gates are within that IC? Maximum 4 or 6 upper?
4, I think so.
4. In a NOT gate, there are 6 logic gates. XOR gate also 4 logic gates. So each and every IC is having less than 10 or maximum 10 logic gates I can have. They are grouped under small scale integrated ICs. In a medium scale integrated IC, I am going to have the range of 10 to 100 logic gates. So which includes a counters, decoders, and encoders. And large scale means it is going to have memories, analog to digital converters. Memories, it can be a dynamic RAM, static RAM, those things I can include. In a very large scale integrated circuits, we are in the process of designing microprocessor units or microcontrollers, you can say anything. So very large scale integrated ICs means which is having in the range of 10,000 or beyond 10,000, I can say. Okay, but here it is mentioned as 1,000 to 10,000. And ultra large scale means I'm going to design a DSP processors. Some specific types of DSP processors are mentioned over here. Digital signal processors, particularly meant for image processing or video processing. They are purchasing. Those processors are categorized as ultra large scale integrated circuit designs. And in the process of very large scale integrated itself, there are different categories are there: bipolar based IC technology, mass based IC technology, BiCMOS based IC technology, and gallium arsenide based IC technologies. There are different in an IC technology. Okay, in an IC technology, which includes I can design SSI M2 ULSI. I can design using bipolar technology. I can design from SSI to ULSI. Similarly, from mass technology also, I can design from SSI to ULSI. It doesn't mean that bipolar can design only SSI or bipolar can design only ULSI. That there is nothing like that. This classification is based upon how many logic gates do I have, but this is completely different based on what is the basic element used for fabricating the circuits. Here in the bipolar based IC technology, bipolar junction transistors, BJT transistors are the basic component. Are using that technology only, they are creating all the circuits. Okay, here the mass is the metal oxide semiconductor based transistors are used as a basic element and used for designing all the logic gates. And here BiCMOS is used for designing all the logic gates, and we are going to deal with the in other way I can say that here we are deciding how many logic gates are used for each and every IC technology, and this discusses about the logic gates, or if the logic gates are built using bipolar technology, these logic gates can be built using mass technology. These logic gates can be built using BiCMOS technology. These logic gates can be built also using gallium arsenide technology. So how do I design a simple logic gate using bipolar technology or mass technology or BiCMOS technology or gallium arsenide technology? So I can design logic gates using any of the technology. But this is about how do I design a logic gate, and this is about how many number of logic gates are used. How many number of logic gates are used? There is a difference between the two things whatever I say now. Okay, so in this slide it is based upon number of logic gates. Here how these logic gates are designed, how these logic gates are designed either using BJT or mass technology or BiCMOS technology or gallium arsenide technology. Do you understood this difference using based upon this slide and this slide? Whether you are able to follow me?
Yes,
Yes or
sir.
no? Okay. I hope in your digital electronic devices course, you might have studied about what is the function of a bipolar junction transistors, what is the function of a mass technology, what is a mass technology, what is the ID versus VGS curve for a mass technology. Those things you might have studied in your previous course. So in the bipolar technology, the basic element is an either NPN transistor or an PNP transistors. Okay, NPN or PNP transistors, which has emitter, base and collector, has the three terminals of this BJT transistors. So based upon number of emitters I have and different connections, how do you connect the bipolar junction transistors? I create emitter coupled logic or transistor logic. 1 minute. I'm sorry. Here the emitter, base and collector, the three terminals are used in the bipolar junction transistors. But in case of mass technology, source, drain and gate, and one more terminal is also there, substrate or body. Okay, any of the terms. So here four terminals are used in the symbol for mass transistors are, this is for NPN transistors, and if I have a bubble at the input, I have an PMOS transistor. So these are the basic elements that are used to design these logic gates. BiCMOS technology, why they went to design, started using BiCMOS technology means there are some disadvantages with the bipolar technology. At the same time, advantages also there with the bipolar technology. For example, the fabrication steps are very difficult in case of bipolar technology. That is a disadvantage. When I talk about advantages of this bipolar technology, the speed of bipolar technology is uncomparable. They are very fast in nature really, because they have high flow of current. Okay, they are using both minority carriers and majority carriers for conduction of current. So that's why the speed is very high in case of bipolar technology, but at the same time the fabrication steps and procedures are very difficult in case of bipolar technology. When I come to mass technology, the fabrication steps is easy. Okay, the fabrication step is easy, the structure is very simple, but the speed is comparatively lower when compared to the bipolar technology. That is the problem with the mass technology. Speed is comparatively low when compared to the bipolar technology. But I can say that actually, if you see the history when compared to bipolar junction and mass transistors also, initially the BJTs are invented. First they came up with the BGT designs only, then they came up with the mass technology. But if you see the history, now when compared to BGTs, most of the circuits they are dealing with the mass technology only. Even though the speed, I said no, the speed of the mass technology is little lower when compared to bipolar junction transistors. Still, we are in a process of using mass technology for making the ICs. Why? I said mass technology is slower, but why still I am sticking on to CMOS based design or mass based design? I said no, one of the advantages of mass technology. What is that? The fabrication steps are easy. The fabrication steps are easy. It is easily able to fabricate. The cost is less, and design process is also easy when compared to the bipolar junction transistors. So that's why the mass started to rule the IC based technologies when compared to the bipolar technology. But still, I should accept that the mass is having a drawback. What is a drawback? it is little bit slower in speed when compared to the bipolar technology. Okay, and in order to overcome the drawback of CMOS and use the advantages of bipolar technology, they started club the technologies. It includes bipolar technology and the CMOS technology. You see here, it started using bipolar BJT transistors and CMOS technology. So it's a combination of BGT and MOS technology. So they started becoming a by CMOS technology. Here also the design cost steps are very tedious. Design process is very tedious, but at the same time the speed will be very good in case of by CMOS technology. Yes. So again, has sorry, I was again having other call with other person. Sorry. Each and every technology has their own advantages and disadvantages. If you want to achieve something, we have to sacrifice something. That is the overall rule, or it's a trade-off between one thing and other thing. Okay. So then they started with the gallium arsenide based technology, where I can go with a high speed at the same time. It is a highly reliable in nature. Reliable in the sense I can use it for space environment or defense environment where heavy ion radiations will be there. Those places also I can use it. Okay, the mobility is also very high in case of gallium arsenide based technology. So these are the different technologies we have based upon what type of transistors I used to design the logic gates or circuits. Okay, and I have one more question. In case of VLSI, or in case of VLSI, here we are discussing everything with respect to logic gates. Here I use 1 to 10, 10 to 100, 100 to 1000, or whatever it is, the numbers I don't bother. Here I always deal with the number of logic gates. For example, I know a subject named analog VLSI. I know a subject named as analog VLSI. Then VLSI means till now we know that based upon number of logic gates only we are classifying it as VLSI. If this range of gates are there, then I'm classifying it as VLSI or low, ultra large scale large scale integrated circuit, like that based upon logic gates if I design. But analog VLSI means that do I need to use logic gates for analog signals? That is not at all possible. Then what do you mean by analog VLSI? Actually, VLSI again it can be classified for two things: analog VLSI and digital VLSI. Digital VLSI only we are going to deal with this course, digital VLSI. Analog VLSI is also there, where analog VLSI is also there. There I am not going to classify it based upon the number of logic gates. Okay, I'm not going to class because I cannot use a logic gate for analog signal processing. I'm going to integrate the number of transistors used for analog signal processing only. It can be an amplifier or a mixer or a down converter or an power amplifier. Those things are comes under analog VLSI. Okay, but the design process is very tedious in analog VLSI when compared to digital VLSI. Very few engineers are working in analog VLSI domain when compared to digital VLSI domain. But this course we are going to deal completely with the digital VLSI. I am not going to touch anything related to analog VLSI course. Okay, so these are the different terminologies are existing. I just want you to let you know about it. Okay, fine. We have detailedly discussed about what are the different things. As I said, why we have to go for VLSI means, as Subhash said, the efficiency or the performance has to be increased. Higher scale, low power consumption, physical, small in size, reduced cost. Okay, so So as I, these are the advantages of why should I go for very large scale integrated circuits. Again, at the same thing I have repeated for advantages of VLSI: small in size, lower cost, low power, high package density, high reliability, and more functionalities are incorporated in terms of advantages of a very large scale integrated circuits. And as I said, I am going to deal completely with the very large scale integrated circuits, that too particularly for digital based VLSI circuits. There I am going to use complementary based technologies. Complementary means it's a combination of both NMOS technology and PMOS technology. NMOS transistors and PMOS transistors, if I use it in the same design, then it is called as complementary MOS based design. Complementary metal oxide semiconductor transistors, or in other words I can say NMOS, okay, n channel MOS transistors, p channel MOS transistors. If I add, which means that I use both NMOS and PMOS, then it becomes a complementary MOS. Okay, complementary MOS transistors, complementary MOS technology. These things I already discussed in wordings. Now I have put them in a slide. That's it. Okay, and okay, nothing to discuss. I don't want to deal anything over here. I will just go over here. Okay, so what is the design hierarchy? For example, I want to design a VLSI chip like this. Okay, I want to design a VLSI chip or a microprocessor or microcontroller like this. Means what are the first step? Where should I stop and how should I proceed with the design procedures? For example, I should know what is the specification. What is the specification of my design? For example, let me start with I am going to design a microcontroller. Means what are the specifications will you give? Can anyone of you say what are the specifications of a microcontroller? What is the internal cache memory, and what are the registers, shift registers I have, and how many bits they are going to handle? What is the data bit I can handle? What is the address bit I can handle? And how many serial ports I can use? What is the baud rate of that serial communication? And what are the other things? What type of arithmetic logical unit I am going to handle, and what is the control unit I am going to handle, and what is the timer I have, either watchdog timer or counter, and many counters are there. No, those counters are how I am going to use them. And what else can I say? Did I missed any one of them? Can any of you point out whatever I missed? Am I speaking too much? Is that convenient for you? Please let me know. I am not discussing anything in detail regarding to VLSI. Till now, I am discussing what are the basics you know in your previous semesters. Okay, you know about BJT, you know about mass transistors, you know about you might not be aware about BiCMOS and gallium arsenide, but you should be aware about what is a bipolar junction transistors and mass technology. And I just introduced these terminologies. Till now, I am discussing that part only. Okay, I hope I am going very slow. Okay, this is about mass technology. We will just don't bother about this slide. Now here we are in the process of design hierarchy. Yes, can anyone of you let me know what else I left here when I asked for a specification of a microprocessor or a microcontroller? Did I mention about
MES
all the
unit,
stuff?
sir.
Enapa?
MES unit, multiple accumulate unit.
I did not get you.
MES is multiply and
Oh,
accumulate
okay,
unit.
okay. MSc Mac multiply and accumulate unit. Okay, fine. So you say these are the specifications I need. What is the size of a shift registers? What is the specification of an ALU? So this comes under a design specification, a system specification. I am going to design a microcontroller. What is the specification of that? And in the abstract level, what do you mean by the abstract level or high level model design? Which means that where I am going to place that block. For example, shift register means where I am going to place it, what is the whether I am going to use JK type of flip flop or SR flip flop, and arithmetic logical unit means whether it is going to deal with the floating type of data or integer type of data. Like that, I am going to give all those specifications to this one. So this is like abstract level, or how I am going to connect them. For example, what is the sequence of steps to be done for reading an instructions? First, let us assume move A comma B. This is the simplest assembly level language what I used to learn when I studied about microprocessor and microcontroller. So what do you mean by that? There are two registers are there. I'm going to read the content from B and I'm going to write it in A. This is about assembly language for 8051 micro controller. Okay, so if I write this instruction, the data from the B register will be read back to the will be copied to the A register. So like that, if I write the instructions, I have to take a memory from the one register. I am going to replace it, or if I write means I am going to take from one memory location. I am going to turn on the LED, whatever I want to do the operation. How the control sequence has to glow. What is the functionality of this control block? All these things are defined in the abstract level of model. What each block is going to do. Here I am saying first design specification means what are the different blocks I need. Okay, what is the size of that in the design specification. In the abstract level definition means the second step is that, and I'm going to define what is the functionality, how they are going to perform the operation. Okay, how they are going to perform the operation, then I'm going to convert them into a logic gate based diagram. I'm going to convert the entire circuit into logic gate based diagram. Now I have to design everything with respect to transistor level. This is with the logic gate, this is with respect to transistors. Either it can be a BJT or a MOS technology or a gallium arsenide technology, whatever technology you call it, I can design it this logic gates using this technology. Here what I am just saying specifications alone, how many shift registers, those things. And here encoder, decoder, muxa, arithmetic logical unit, how they are connected, those things I have to define it in the abstraction level. So these encoders, decoders, arithmetic logical units, counters, shift registers are designed using this logic gate. Again, from the logic gate, how do these logic gates are designed? Using the transistors, I am designing these logic gates. Okay, and how I am placing the, for example, layout designing. Layout means which a transistor has to be placed where, how I am going to connect the transistors. I hope this is similarly like a PCB designing. Okay, but I am not going to design a PCB, I am going to design an IC. Okay, within an IC, how do I place the components, how do I wire them, that is about physical designing. Once I decide which component has to be placed where, I am going to manufacture it or fabricate it. Finally I will be having an IC over here. So these are the design procedures I have to follow. So first, what is the step? Design specification, abstract level definition, logical design, circuit design, and then physical design. I'm not writing the entire statement, I'm just writing the few letters in order to have a just understanding about it. After physical designing, I'm going to manufacture it. Finally I have a chip in my hand. So these are the steps I have to follow for any of the IC design you have to designing. Design specification means what is the specification of my microprocessor or microcontroller, and what are the components, how I am going to design it. Okay, and gate, I mean sorry, encoder or decoder or shift registers or ring counter or Johnson counter or those things are defined over here. How I am going to design those blocks using logic gates. Logic gates, how I am going to design this logic gates using transistors. Here I can use either a bipolar technology or MOS technology or gallium arsenide technology, whatever technology. Okay, then using these transistors, how I am going to design a layout of that. Layout means, for example, if I want to design a layout means, I hope you should be aware about what is meant by PCB designing. Here I will be having IC, here I will be having an IC, I will be connecting wires, and here I will be having some wires. I have to take a power connection from all over the place, ground connection. So different ICs are placed. This is about PCB designing. PCB designing. The same way within an IC also I can connect the transistors. For example, I have one transistor here, I have some resistor here, I have one power supply. So I can place the components at the transistor level. How do I connect it in an IC, in a chip? How I am going to connect it? That is about physical designing. It includes floor planning, routing, placement. Many things are involved over there. Okay. And finally, I am going to fabricate that IC. After fabricating, testing, I will be having a final chip in my hand. So these are the design process I have to follow in designing a simple VLSI IC. Okay, just if I want a simple IC means these are the design process every IC has to follow. Was these steps clear for everyone? Yes or no?
Yes, sir.
Okay, okay, fine. So we have discussed about what are the design hierarchy. Again, there are two methods of approach. What do you mean by there are first approach is about top-down approach, and the other method is about bottom-up approach. The top-down approach means, for example, I hope in the last lab, in the yesterday's lab, we started designing an half adder. We started designing. This is a top-level design. In order to design an half adder, first I need to design an XOR gate. First I need to design an XOR gate and AND gate. Okay, so for example, if I want to design a full adder means what should I need? I need two half adders. I need two half adders. So this is an abstract level, sum carry input, sum, so a b c in, and sum and carry out are the outputs. This is for a full adder. Within a full adder I need two half adders. I need two half adders. So first I am designing as one half adder, and within a half adder, in order to design a half adder, I need XOR gate and AND gates, and I need to design an OR gate also because I am using a full adder. So I am designing first an என்னப்பா என்னப்பா hello hello, someone was saying something, I cannot hear you properly, please can you repeat? Surya, Talari Surya pa, roll number 45, what happened?
Sir, nothing, sir. By mistake, mic is on.
Okay. So first I am going to design a full adder. Using full adder, in order to design a full adder, I need half adder. In order to design a half adder, I need XOR gate, AND gate, and OR gates. So this is the topmost design. This is the top. First, I need to design a full adder. So based upon the full adder requirement, I am designing a half adder. Within a half adder, I need to design XOR gate and gate. So how does the design goes? Full adder, half adder, half adder, XOR gate, AND gate, AND gate, OR gate. So the design process goes in this order. First full adder, then half adder, then half adder to XOR gate. I think everything comes under one logic gates. Okay, I can just say it as I am going to design the basic logic gates. And how I am going to design these logic gates? I am going to design all these logic gates using CMOS technology. Finally, at transistor level, I got the design. So this is the flow if you are following the top-down approach. First, topmost level, what I want to design, I am going to design a full adder. From the topmost circuit level, finally, I am ending at the CMOS transistor level circuit diagram. This is about top to bottom approach. Top to bottom approach. Top to bottom approach. The other way is there. Other way is there. What do you mean by that? So first I will design logic gates. All the basic logic gates I will design using MOS technology. Okay, which means that I will design an AND gate, OR gate, XOR gate, NOT gate. Every logic gates I will design using CMOS technology. Among the existing logic gates, first I will design a half adder, and using half adder I can design a full adder. So first in the bottom up approach, in the bottom to top approach, first using transistors I will design a logic gates, and using logic gates I will design some basic building blocks like a half adder, and using half adders whatever I can design it. So here I took half adder and full adder as an example. It doesn't mean that always using logic gates I can design using an half adder. Instead of that half adder I can design using encoder also. I can design. I can design an encoder, I can design decoder, I can design mux, I can design flip flops, anything I can design. So basically there are two methods. That's what I said. In the bottom up approach, I start up with building the basic components and then I go for the higher abstraction level. In the top to bottom approach, I know what I need. From that, I started designing the basic components. Was it clear? What is the difference between top to bottom approach and bottom to top approach? Was this step clear for everyone? And don't
Yes.
bother about the statements, whatever I write over there. You just understand. I am not reading whatever is already typed over here. If you are ready to read it, why should I explain it about it? So don't bother about the wordings. I am not looking on the wordings at all. I'm just looking on the title alone. You should know the basic logic behind it. The theory you have to read from the slide or from the textbook, that has to be for exam purpose. But now I am not going to deal with exam purpose. I am just want you to understand what is a top down approach and bottom to top approach. Was that step clear for you or not? Is it fine? Do you have any doubts? Yes, yes, yes. Please let me know. Avantika, can you hear me?
Yes, sir. It was clear, sir.
Okay. So, Avantika, if I ask you to design an encoder
Yes.
using bottom to top approach, what are the things you will follow?
Sir, again, for bottom to top, we'll be designing the basic gates and all.
Very good. Using basic logic gates, what will you design?
Uh, like using that, we'll be
We know the Boolean expression means we can just connect to the
yes,
circuit using logic gates, correct?
yes, sir, yes,
Yes or no?
yes, sir.
Yes. So that is what I also intended to do that. So first for a bottom to top approach means first you design the basic logic gates, and if you have a set of logic gates, you just connect it based upon your availability. In the top to bottom approach, first you create an uh, truth table. From the truth table you know what is a boolean expression. From the boolean expression you will come to know what are the AND gate, OR gate or XOR gate required, and then you design it the logic gates, and then from the desired logic gates you design what are the transistors required, how many transistors are required to design that particular logic gates. Like that, there are two methods. Okay, so that's how we are two methods of designing an IC also, top to bottom approach and a bottom to top approach. So the same thing as I have written over here. Then tomorrow we will discuss about what are the different categories. Again, one more classifications in VLSI IC design. Okay, full custom design, semi-custom design, and application specific integrated circuit design. I am repeating it once again. If you are not able to follow me, please let me know. These are very preliminary classes. I am discussing completely theory part. Okay, 90 percentage is known to you in previous semesters. I am trying to reiterate the same thing in a different manner. That's it. Okay, you know about logic gates, you know about ICs, you know about PCB designing. Not a complete design, but you know what it is. Okay, I am trying to merge all the things in a single point. Okay, that is what I am doing till now. I have not entered into the. I hope I entered 0.1 percentage into the syllabus. I am not entered completely, but I am just creating an loophole for entering into the subject. Okay, thank you for today's class. If you are having any difficulty, please let me know. If you have any doubts also, please let me know. Don't say at the end of the semester. Thank you all. See you. Bye.
Thank you, sir.
Thank you, sir.
Yes.
Thank you, sir.
Thank you. Thank you. Bye.
Thank you, sir.
Thank you, sir.